Exchanges of rock between planets in our own solar system like Earth and Mars is a fact, and quite common. We've found Mars rocks here, and it's safe to assume there are Earth rocks on Mars. If biomatter hitched a ride on those rocks, and the conditions were right, life would evolve. Mars was once very Earth-like, with a stable climate and lots of surface water. If microbes evolved there, they very well could have ended up here. In 1996, a meteorite from Mars was examined under a microscope. It appeared to contain fossilized microbes. It's a controversial claim, but with what we now know about comets, life on Mars seems very plausible.
Today, Rock 84001 speaks to us across all those billions of years and millions of miles. It speaks of the possibility of life. If this discovery is confirmed, it will surely be one of the most stunning insights into our universe that science has ever uncovered. Its implications are as far-reaching and awe-inspiring as can be imagined.
If life evolved in our solar system, then chances are it's going to be found everywhere where the conditions exist to support it. Now, it's liquid methane, not water, but life could evolve there. Recent studies show Venus could support microbial life in the upper layers of its atmosphere. And Ceres, a dwarf planet in the asteroid belt, has water ice, and there's evidence of liquid salt water below the surface. And these are places right here in our solar system. But if we look further out, the chances of life increase tremendously. The number of potential Earth-like planets in our galaxy is about 100 billion. And there are about 100 billion other galaxies out there. So the total number of planets that could support life is incomprehensible. And with all the asteroids flying around our galaxy carrying the seeds of life, panspermia doesn't sound like pseudoscience. In fact, life being delivered here via panspermia is the only theory, to me, that makes sense. Life not arising on Earth, but arriving on Earth. It's a fascinating theory, but is it true? Well, a couple of factors make seeding life on Earth a challenge. The time required for biologically active rocks to be ejected from a solar system is probably the biggest obstacle. It could take between 4 and 50 million years for rocks to break from a planet and leave the solar system. But if a planet is hit with a big enough object, like the asteroid that killed the dinosaurs, it can throw rock into orbit in an instant. In the early solar system, giant impacts like this were happening all the time on every planet. But life finding its way here from another star, that's a long shot. Not impossible, but very difficult. But life finding its way here from Mars or Venus, that's no problem at all. Another issue though, no matter the distance traveled, the biological matter has to stay viable for the journey, for millions or billions of years. And the size of the rock really matters. We know that bacteria and even more complex forms of life can stay dormant for many years, but that doesn't do you any good if your rock vaporizes when hitting the Earth's atmosphere. You're gonna need a pretty big rock to get through. Again, not impossible, but not easy. Unless you adopt the theory of direct panspermia, which answers all these concerns. The discovery of the structure of DNA is credited to James Watson and Francis Crick, so reputable and respected scientists. In 1971, they spoke at a conference on communication with extraterrestrial intelligence organized by Carl Sagan. They claimed organisms were deliberately transmitted directly to the Earth by intelligent beings from another planet. No randomness was involved. The seeds of life made it here because this is where they were sent. Simple enough, but in the end, panspermia means that we're not from here. And you'd think, like the octopus, there'd be evidence within us that maybe the Earth isn't our original home. Well, Francis Crick actually suggested there is evidence. In 1973, he published the paper with Leslie Orgel, a molecular biologist. The paper was called Directed Panspermia. The paper says that the chemical composition of living organisms, and I quote, must reflect to some extent the composition of the environment in which they evolved. The paper makes the point that human beings have a trace element in their bodies called molybdenum, which is crucial to organic processes. But here's the thing, molybdenum is pretty rare on Earth. But you know what's a great source of it? Meteorites. So maybe somewhere out there is our home planet, where molybdenum is plentiful, and the fact that we can survive on Earth makes us another extremophile.